In Lesson 6, we're going to continue with polynomial multiplication to start. But I'm going to take a little bit of a break from the algebra and look at some of the geometry behind the polynomial multiplication we've been discussing. I'm going to start by working a couple of basic geometry examples, do a couple of applications, and finally talk about perfect square trinomials. Let's start with the basic geometry examples. In the next two examples I'm going to do, we want to start by expressing the area of the outer rectangle as the product of two binomials, then find the sum of the area of the four smaller rectangles in the picture, and finally use polynomial multiplication to show that the two expressions are equivalent. We're going to see a relationship between geometry and algebra in these examples. So let's start. We're first asked to express the area of the outer rectangle as the product of two binomials. Now typically we don't think about rectangles and binomials in the same thought. Remember that the area of a rectangle is just the product of its length and width. Well, what's the length of this rectangle? Well, we have the little purple rectangle, which is 3x units long, and the green rectangle, which is 1 unit long. So the length of the outer rectangle is 3x plus 1. What about its width? Its width is x plus 3. So to write the area of this outer rectangle, we can write it as the product of two binomials. So for part A, the area of the outer rectangle is the product of its length times the width, 3x plus 1 times x plus 3. Now we're going to find the sum of the areas of the four smaller rectangles. Well, let's look at the purple rectangle. Its length times its width gives us 3x squared. Let's look at the gray rectangle down below the purple one. Length times width, 3x times 3, that equals 9x. Looking at the green rectangle, the area of that rectangle is x times 1, x units. Finally, the area of the yellow rectangle, 3 times 1, is 3. Now what we're asked to do is to find the sum of the area of these four smaller rectangles. Well, let's write it down. The sum of the area is 3x squared plus 9x plus x plus 3. Finally, we're asked to use polynomial multiplication to show that the expressions from these two parts are equivalent. Well, let's start with the product of the two binomials. Finding the product of the first terms, we get 3x squared. Finding the product of the outside terms, we get 9x. Finding the product of the inside terms, that's 1x. And finding the product of the last terms, that's 3. Notice the geometry is showing us that these two areas are equivalent, and the algebra is showing us that these two algebraic expressions are equivalent. Let's just do this one more time. Same trick. We're going to express the area of the outer rectangle as the product of two binomials. So in this case, the area of the outer rectangle is going to be its length times its width. In this case, along the top, if we call that length, that will be x plus 2, and down the side, we see that that length is 2x plus 3. We're going to do the same thing. We want to find the sum of the area of the four smaller rectangles. So the sum of the areas is, let's look at what we have. We have 2x times x, that's 2x squared, plus 3 times x, 3x, plus 2x times 2, that's 4x. Finally, plus 3 times 2 is 6. Now, what we're looking at here is sort of a geometric interpretation of the algebra we were doing in the last lesson. So finally, we're going to do the algebra to show that these two areas, which are equivalent, are the same as the two algebraic expressions being equivalent. So if I expand x plus 2 times 2x plus 3, using the FOIL shortcut, x times 2x is 2x squared. Product of the outer terms gives me 3x. Product of the inner terms gives me plus 4x. And finally, the product of the last terms gives me plus 6. Indeed, I see that the geometry and the algebra are coming together. Here's another example, and you may see problems like this in your textbook. We're asked to express the area of the shaded region as a polynomial written in descending powers of x. So let's think about how we're going to find the area of that shaded region. If we find the area of this outer rectangle and take away the area of this inner rectangle, we're taking away the whole, and we're going to be left with this shaded region. So if I find the area of the outer rectangle and subtract the area of the inner rectangle, I will have the area of the shaded region. So let's do that. So the area of the shaded region is the area of the outer rectangle, which is the length times the width, minus the area of the inner rectangle, which is minus 4x. Let's simplify this. Using the distributive property, 2x times x is 2x squared, plus 2x times 4, that's 8x, minus 4x. And simplifying, I get 2x squared plus 4x. The polynomial expression I have is already written in descending powers of x. Now we can do a little bit more with this problem. We did what the problem asked, but one of the things that's kind of cool about looking at the geometry is we can kind of move that hole around. Suppose I move that hole over to the corner of the outer rectangle. Let's look at this problem another way. If I draw this line here, I know the length of the whole outer rectangle is 2x. Here's 1x, so this length must be x as well. Let's draw this line. The whole width is x plus 4. I have 4 units here. This dotted line, the vertical dotted line, must also have length x. Let's calculate the area of these 3 purple parts. We have x squared, and that last purple rectangle has an area of 4x. We can see that this is 2x squared plus 4x. One more example, similar to the last. Let's express the area of this shaded region as a polynomial. Strategy is going to be just what we did in the last problem. We're going to take the area of the outer square and subtract the area of the inner square. So the area of the shaded region is x plus 4 quantity squared minus x squared. So let's remember that we're going to need to expand x plus 4 quantity squared using a plus b squared equals a squared plus 2ab plus b squared. So I have x squared plus 8x plus 16, and I'm going to subtract x squared. Notice in this expression, the x squared terms cancel, and I'm left with 8x plus 16. The important thing to recognize here is that when I subtract x squared from x plus 4 quantity squared, I'm not getting 16. I get 8x plus 16. Now, one of the things you might want to do is kind of move around this picture a little bit like we did in the last example to show yourself that the algebra and the geometry are related and that we do indeed get 8x plus 16. So let's just do 2 applications. A frame shop regularly frames square paintings of variable size using a 1-inch frame. We're asked to find an algebraic expression for the area of the frame in terms of the size of the painting. Well, this is a mouthful. Let's draw a picture of what we have here. We have a square painting. The square painting is of variable size, so we're going to call the length of the side of the painting x. Now we have a 1-inch frame. So on each side, we're going to add 1 inch. On the top and the bottom, we're going to add 1 inch. So the distance across now is x plus 2. The distance from top to bottom is x plus 2. To find the area of the frame, we're going to do the exact same algebra we just did in the last example. So let's do it. I'm going to take the area of the outer square, which in this case is x plus 2 quantity squared, and I'm going to subtract the area of the painting, which is the inner square, which is x squared. Again, recalling that I need to expand x plus 2 quantity squared, I get x squared plus 4x plus 4, and I'm subtracting x squared. Notice the square terms cancel, and I'm left with 4x plus 4. So now the frame shop can figure out exactly how much material they'll need for the frame based on the size of the painting. Let's look at another application. Here we have a shipping company, and it wants to construct boxes of various heights using cardboard that's 36 inches by 24 inches. We're being asked to find an algebraic expression for the volume of the box in terms of the height of the box. Again, this is a mouthful. Let's draw a picture. We're going to start with our piece of cardboard. Our cardboard is 24 inches by 36 inches. Now, how are we going to get a box out of this? Let's suppose the shipping company wants a box that's 4 inches high. What they could do is measure off squares in each corner. The size of the squares would be 4-inch squares. Well, why would they do this? Look at what happens. If you cut out those squares and then fold the cardboard along those dotted lines, you're going to get a 3-dimensional box. This box is going to have a height of 4 inches. Let's generalize this a little bit. Suppose the shipping company wants a box that's 8 inches high. We're just going to change the 4 inches to an h. Now, let's recall the formula for the volume of this box. The volume of a rectangular box is going to be the product of its length, width, and height. Well, we know what the height is. The height's going to be h inches. Now we have to think about the length and the width of this box. Let's start with the long side. Originally, we had 36 inches of cardboard, or a side was 36 inches. And what we did is we cut out these corners, which were h inches square. So what I'm left with is 36 minus 2h as the length of the actual box. Same sort of argument applies to the width. We started out with 24 inches, but we cut out these 2 squares. So we're interested in just this length for the width of our box. And that's going to be 24 minus 2h. Now we're ready to find an algebraic expression for the volume of this box. So the volume of the box is, let's just write V for volume. It's going to be the length, which is 36 minus 2h, times the width, which is 24 minus 2h, times the height. We've been practicing multiplying binomials, so let's expand this. I'm going to start by using the distributive property with the last 2 factors. So I'm going to leave the first factor as is and distribute the h across the 2 terms in the second factor. So I have 24h minus 2h squared. Now I'll use FOIL. I have 2 binomials. So I have product of the first terms, 36 times 24h, that's 864h. Product of the outside terms, that's minus 72h squared. The product of the inside terms, negative 2h times 24h, is negative 48h squared. And finally, the product of the last 2 terms, negative 2h times negative 2h squared, is plus 4h cubed. Now I want to simplify this. I'm going to write my formula for the volume of the box in descending powers of h. So my highest order term is 4h cubed. I have 2h squared terms. Negative 72 minus 48 is negative 120 h squared. And finally, I have just one first-degree term, plus 864h. So now, the company can figure out exactly the capacity of the box based on the height they want for the box. They just plug the height into the formula. They know the box's capacity. I'm going to finish off this part of the lesson by talking about perfect square trinomials. We're going to do exactly the same thing with this problem as we did in the first couple of examples in this lesson. First thing we're going to do is express the area of the outer square as the product of two binomials. Well, now we have a square. The side of the square is a plus b. So the area of the outer square is a plus b quantity squared. The area of a square is just its side squared. Now let's find the sum of the area of the four smaller rectangles. So the sum of the areas is, let's look at the purple rectangle, which is a square. A times a is a squared. Then I have a b squared. And I have two rectangles of area AB. There's two of them. So I'm going to write this as 2AB. Now you may wonder, why did I write things in that order? That's because we have a formula for writing the product of a plus b quantity squared. Remember what that formula is. That formula tells us that a plus b quantity squared is a squared plus 2ab plus b squared. You derive this formula by just applying FOIL to the binomial a plus b times a plus b. Now we see that there's a geometry behind this. In fact, there are a lot of squares here. And in fact, when we add a squared plus b squared plus 2ab, we get another square. This is called a perfect square trinomial. So trinomials of this form, a squared plus 2ab plus b squared, are called perfect square trinomials because they can be written as a plus b quantity squared. So here's an example of a perfect square trinomial. This actually could be written as x plus 4 quantity squared. Expand that and you'll see that these two expressions are equivalent. Here's another perfect square trinomial. In this case, we have x squared plus 20x plus 100. This is equivalent to x plus 10 quantity squared. Now we can also have a perfect square trinomial when we have an expression of the form a squared minus 2ab plus b squared, because this is just equivalent to the quantity a minus b quantity squared. Here's an example of another perfect square trinomial. One last example. Let's consider the expression x squared plus 10x. But let's consider it geometrically because that's what we've been doing in this part of the lesson. Here's a picture of x squared plus 10x. Now there's more than one way to draw this picture, but I chose to draw it the way we've been looking at these squares in this lesson. We have a purple square that has an area of x squared, and we have two rectangles. The area of each rectangle is 5x. We've got two of them. So here's a picture of x squared plus 10x. Now we can ask a question like this. What number can be added to the expression to obtain a perfect square? Well, if I want a perfect square out of my picture, I could just kind of fill in this corner. And what is the area of that corner square? Well, it's 5 times 5, or 25. So what I can write is x squared plus 10x plus 25. That's a perfect square trinomial. And in fact, this is equivalent to x plus 5 quantity squared. In a later math class, you might be starting with an expression like x squared plus 10x, and you'll be asked to complete the square. When you go through the process of completing the square, you are actually completing a geometric square. We had these 3 little bits with a part missing, which we completed by just kind of figuring out what the area of this missing corner of the square was. You'll come back to this in a later math class, but I just wanted to show you the picture behind completing the square. Now I'm going to turn this over to Steve, who's going to work a little bit with polynomial division.
Hello. As Anne promised, in this part of the lesson, I'm going to talk about polynomial division. I'm going to limit my discussion to dividing polynomials by monomials. Before I can begin discussing polynomial division, I need to talk about another rule of exponents called the quotient rule. And then we're going to see some examples of monomials divided by monomials. And finally, we're going to take other polynomials, polynomials with more than one term, and divide them by monomials. Last week, we talked about 3 rules of exponents. Here's a 4th rule. It's called the quotient rule. Let's look at the expression x to the 7th over x cubed, and let's think about what this really means. Well, in the numerator, we have x to the 7th, which is 7 factors of x, and in the denominator, we have x cubed, which is 3 factors of x. What I am going to do here is I'm going to take this single fraction and I'm going to turn it into the product of 2 fractions. Remember, when you're multiplying fractions, you multiply the numerators by the numerators and the denominators by the denominators. So when I break this up into 2 fractions, I want to make sure that between the 2 fractions, there's 7 factors of x in the numerator, and between the 2 fractions, there's 3 factors of x in the denominator. Now I'm going to be very deliberate about this. Since I have 3 factors of x in the denominator, I think the first fraction I pull out is going to be x cubed over x cubed, because that will simplify to 1. Now when I pull out the 3 factors of x from both the numerator and the denominator, I have 3 factors of x over 3 factors of x, and what I leave behind is 4 factors of x in the numerator and no factors of x in the denominator. Of course, in my fraction, x to the 4th, I can't have a denominator with nothing, so I'm going to put a placeholder of 1 down there. Now, as I mentioned earlier, the whole reason I'm doing this is because the 3 factors of x divided by 3 factors of x is simply 1. So what I have here is 3 factors of x over 3 factors of x, which is 1, multiplied by 4 factors of x over 1. 4 factors of x divided by 1 is simply 4 factors of x. Where did those 4 factors of x come from? They came from the 7 factors of x that I originally had in the numerator, divided by the 3 factors of x that I had in the denominator. That left me with 7 minus 3, which is 4 factors of x. How do we express 7 minus 3 factors of x? We express that with an exponent of 7 minus 3. So this suggests a rule for us, and the rule that it suggests is called the quotient rule for exponents. And the quotient rule for exponents says that if you have x to the m divided by x to the n, to simplify that, you want to write that as x to the m minus n. Let's see this rule put into action a few times. Let's simplify x to the 12th over x to the 5th. Well, we have a new rule that we can apply. It's called the quotient rule of exponents. The quotient rule of exponents says that we can simplify this if we write a single occurrence of x and make an exponent of the numerator's exponent minus the denominator's exponent. In other words, an exponent of 12 minus 5. So this all simplifies to x to the 7th. Let's think about it. Does this make sense? I think so. We have 12 factors of x in the numerator and 5 factors of x in the denominator. When we pair up factors of x from the numerator and the denominator, we will be able to factor out 5 occurrences of 1, x over x, 5 times, and then we'll be left with 12 minus 5, which is 7 factors of x in the numerator. Let's apply the rule to the expression t to the 36 over t to the 21st. T to the 36 over t to the 21st is equivalent to t to the 36 minus 21, and I'm pretty sure that 36 minus 21 is 15, so this simplifies to t to the 15th. Those 21 factors of t in the denominator canceled 21 factors of t in the numerator and left behind 15 factors of t in the numerator. Now this problem looks awfully similar to the last two problems that we worked. Actually, what we've done in this problem is we've taken the last two problems and turned them into one problem. We have x to the 12th, t to the 36, over x to the 5th, t to the 21st. The first step in simplifying this expression is to, in a sense, turn it back into two problems. What I'm going to do is I'm going to write this single fraction as the product of two fractions. I'm going to write a fraction involving the x factors, and I'm going to write another fraction involving the t factors. And since the way we multiply fractions is by multiplying the numerators together and the denominators together, when I split this up into two fractions, my x fraction is going to be x to the 12th over x to the 5th, and my t fraction is going to be t to the 36 over t to the 21st. Now we just saw on the last screen that x to the 12th divided by x to the 5th is x to the 7th, and t to the 36th divided by t to the 21st is t to the 15th. So our original expression simplifies to x to the 7th times t to the 15th. This process of pairing like factors from the numerator with like factors from the denominator is a key step in what we call dividing monomials into monomials. So let's see some more examples of that. Let's talk about dividing monomials by monomials. Let's simplify 15x to the 12th, y to the 4th, z to the 6th, divided by 5x cubed z. Now the first thing I want to establish is, what do I even mean by simplify? Well, the word simplify applied to an algebraic expression actually has a lot of different meanings. But when you're talking about simplifying a single term, and this is a single term because there is no addition or subtraction going on anywhere in the expression, one of the things that the word simplify means is that a term is not simplified if any variable appears in the term more than once. Now you can't really say the variable doesn't occur more than once because x to the 12th, that's 12 occurrences of x, but if we simplified this and we had x written to the 12th, the variable x would only be appearing in the expression once. So what we want to do is we want to take our two appearances of x and turn it into a single appearance of x, and we want to take our two appearances of z and turn it into a single appearance of z. So let's set about doing that. We're starting with 15x to the 12th, y to the 4th, z to the 6th, and we're dividing that by 5x cubed z. The first step in the simplification process is to break this up into the product of several fractions. We want to pair the variable factors in the numerator with the similar lettered variable factors in the denominator, and we also want to pair the coefficient from the numerator with the coefficient in the denominator. So our coefficients are going to be 15 over 5. Now we want to multiply that by our x fraction. That's going to be x to the 12th divided by x cubed. How about our y factors? Well, there's a y factor in the numerator. There is no y factor in the denominator. But if I want to write this as a fraction, all I need to do is introduce a denominator of 1, because y to the 4th divided by 1 is equivalent to y to the 4th. And then we have our z factors, which are z to the 6th divided by z. Now let's go ahead and simplify every one of these mini fractions in our product. 15 divided by 5 is 3. X to the 12th divided by x cubed is x to the 9th. There's a couple ways I can come up with that. I can use the quotient rule for exponents that says x to the 12th divided by x cubed is x to the 12 minus 3, or I could just think about how many common factors of x do I have. The 3 factors of x in the denominator cancel 3 of the factors of x in the numerator, leaving me with 12 minus 3, which is 9 factors of x in the numerator. Y to the 4th divided by 1, well, that's just y to the 4th. Z to the 6th divided by 1 factor of z leaves behind z to the 5th. there's another way that I can see that that last factor is just z to the 5th. I can think of z as z to the 1st power. And the quotient rule of exponents says that z to the 6th divided by z to the 1 simplifies to z to the 6 minus 1 power. Let's simplify this monomial divided by a monomial. Our numerator is minus 48 t to the 44th w to the 8th a, and we're dividing that by a denominator of minus 6 t to the 43rd w to the 7th. Let's begin by pairing up our coefficients and our like variables. Minus 48 divided by minus 6, that's going to be the coefficient. Let's multiply that by t to the 44th divided by t to the 43rd. Let's multiply that by w to the 8th divided by w to the 7th. And finally, in terms of my a factors, I only have a factor of a in the numerator, but a is equivalent to a over 1, and I think I'll go ahead and write it that way to make sure that I line things up correctly when I multiply my fractions together. Negative 48 over negative 6 is positive 8. T to the 44 divided by t to the 43rd, once I'm done canceling 43 factors of t from the numerator and denominator, I'm only left with one factor of t in the numerator. 44 minus 43 is 1. W to the 8th over w to the 7th. Subtracting 7 factors from 8 factors leaves you with one factor. A over 1 is a. This is 8TWA. Let's do another problem. Let's divide 21x to the 7th, y to the 11th, z to the 52nd by negative 6x, y squared, z cubed. We could use a division symbol to indicate that we're going to perform this division, but in algebra it's much, much simpler if you go ahead and indicate division with a fraction bar, because we have several rules of algebra that apply to fractions. So I'm going to begin by writing 21x to the 7th, y to the 11th, z to the 52nd as the numerator of a fraction whose denominator is negative 6x y squared z cubed. Now the next step is I could literally write down 21 over negative 6 times x to the 7th over x times y to the 11th over y squared times z to the 52nd over z cubed. But I'm going to see if I can imagine that step in my head and go ahead and write down the simplification that I would get after applying that step. The coefficient would be 21 divided by negative 6. 21 and 6 are both evenly divisible by 3. And when I factor out 3 over 3, I leave behind a factor of 7 in the numerator and a factor of 2 in the denominator. So the coefficient on the simplification here is going to be negative 7/2. If I take 7 factors of x and I divide out 1 factor of x, I leave behind 6 factors of x. If I take 11 factors of y and I divide out 2 of those factors of y, I leave behind 11 minus 2, which is 9 factors of y to the 9th power. 52 factors of z divided by 3 factors of z leaves behind 52 minus 3, which is 49 factors of z, or z to the 49th power. Now, some of you, especially at first, would really be helped if you went ahead and wrote down this step, breaking it up into 4 fractions, the product of 4 fractions, before doing the simplification. That's great. The reason I chose not to write that step is because I want you to encourage you that after you've done several practice problems, see if you can be successful without writing this middle step down. It'll save you a lot of time in the long run, and if you don't try, you'll never know. But remember, if you're more successful writing out this step, then every single time you want to write out the step because you want to be successful. Now let's talk about dividing polynomials with more than one term by monomials. Let's simplify 7x to the fourth plus 4x cubed minus 12x squared plus x divided by x. So we'll begin by writing down our original problem. And our first step after that is very similar to the first step that we used when we were dividing monomials by monomials. When we were dividing monomials by monomials, we took the single fraction and turned it into the product of several fractions. What we're going to do here is we're going to take the single fraction and turn it into the sum and difference of several fractions. But there's something a little bit different when you take a single fraction and turn it into the sum and difference of several fractions. When you're adding together fractions and you have a common denominator, the way that you add the fractions is you find the sum and difference of the numerators all over the common denominator. So when you go in the opposite direction, every single term in the numerator needs to get its own occurrence of the common denominator. And that's all a very, very wordy way of saying that when I break this up into the sum and difference of several fractions, each fraction needs a denominator of x. I need to write this as 7x to the fourth divided by x plus 4x cubed divided by x minus 12x squared divided by x plus x divided by x. Now let's go ahead and simplify the four monomial divided by monomial terms. The first monomial divided by monomial term is 7x to the fourth divided by x. Since there's a coefficient of 1 in the denominator, it's pretty easy to figure out that the coefficient of this division is going to be 7. If I take x to the fourth and divide out one factor of x, that leaves behind x cubed. 4x cubed divided by x, well, the coefficient's going to be 4. Xxx over x, when I factor out x over x, I leave xx in the numerator. I have x squared. Then I have minus 12. X to the 2 divided by x to the 1 is x to the 2 minus 1, which is x to the first power, which we normally just call x. And x divided by x is 1. Now, a thought may have occurred to you as I was working through all of these examples. What about dividing by 0? Like in this case, what if x was 0? Well, if x was 0, we actually couldn't work this problem because we would be dividing by 0, which is undefined. So whenever you're asked to divide one monomial by another monomial, there's an assumption, and the assumption is that when you get your simplification, you're only going to replace the variables by values that would not result in a 0 occurring in the denominator of the fraction. Holy smokes. This problem has this effect on very, very many people. They start freaking out. This looks like a really hard problem. That is a natural reaction. So before I begin working through this problem, I want to talk about some things that you might do if you start freaking out when you see a problem that looks like this. The first thing you want to do is you want to relax. And something that might help you relax is to take a deep breath. And while you're taking your deep breath, try having pleasant thoughts. And ultimately, at the end of your pleasant thoughts, try and remind yourself that as long as you attack the problem one step at a time and you don't make any errors, you'll eventually get to the correct answer. So with this nice positive attitude, let's attack this problem one step at a time and see if we can come up with the correct simplification of this pretty scary looking expression. So we need to begin by writing down our scary looking expression, which is negative 72 xy to the 27th plus 81 x cubed y to the 12th minus 36 x to the 5th y to the 9th, and this is all being divided by the monomial negative 9 x y to the 7th. The first step of simplifying a multi-termed polynomial divided by a monomial is to break your original expression into the sum and difference of fractions that are simply monomials divided by monomials. And all of that is just a long way of saying that I'm going to take every term in the numerator and give it its own personal privatized denominator of -9xy to the 7th. So let's do that. When I do that, I'm going to have -72xy to the 27th divided by -9xy to the 7th plus 81x cubed y to the 12th divided by -9xy to the 7th minus 36x to the 5th y to the 9th divided by -9xy to the 7th. Now, just taking this one step has taken this problem, and for me anyway, taken it from pretty frightening looking to actually not so bad looking. And let me tell you why, to me, this problem now looks a whole lot easier. Because I'm not seeing one problem anymore. I'm seeing three problems. I'm seeing three problems where I need to take a monomial and divide by a monomial. The first problem I'm seeing is -72xy to the 27th divided by -9xy to the 7th. The second problem I'm seeing is 81x cubed y to the 12th divided by -9xy to the 7th. And the third problem I'm seeing is 36x to the 5th y to the 9th divided by -9xy to the 7th. The only thing I need to do in addition to working those three problems is to remember to put a plus sign between the first two results and a subtraction sign between the second two results. So let's go ahead and do that. So my first monomial divided by monomial, the coefficient is going to be -72 divided by -9, which is +8. How about my x factors? I have one x factor in the numerator, one x factor in the denominator. X over x is 1. Multiplying by 1 does not change the result. You never need to write down a multiplicative factor of 1. How about y to the 27th divided by y to the 7th? That leaves behind 20 factors of y to the 20th. How about my middle term? Well, let's first think about the coefficient. 81 divided by -9 is -9. I need to add -9, so that's the same as -9. X cubed divided by x, that's 3 factors of x, take away 1 factor of x, leaves behind x squared. Y to the 12th divided by y to the 7th is y to the 12 minus 7, which is y to the 5th. How about my final term? 36 over -9 is -4. Subtracting -4 makes the coefficient +4. X to the 5th over x, that's x to the 4th. Y to the 9th over y to the 7th, that's y squared. Let's simplify this division. This is stated using a division symbol. We don't really have a whole lot of rules for simplifying algebraic expressions using a division symbol. We do have a whole lot of rules for simplifying algebraic fractions. So the first thing I'm going to do is rewrite this as a fraction. -11a cubed b to the 11th plus 14a cubed b to the 8th minus 12a cubed b cubed, all of that divided by 8a cubed b cubed. Might look pretty scary. If it does, take a breath, think nice positive thoughts, and remember one step at a time. And the first step is to break this up into the sum and difference of several monomial over monomial fractions. In this case, that's going to be -11a cubed b to the 11th divided by 8a cubed b cubed plus 14a cubed b to the 8th divided by 8a cubed b cubed minus 12a cubed b cubed divided by 8a cubed b cubed. Now, in a sense, we have three problems. The first monomial over monomial, the coefficient is a negative 11 over 8, which is negative 11 eighths. A cubed over a cubed, that's a multiplicative factor of 1, so we don't need to write anything down. B to the 11th over b cubed is b to the 8th. Plus 14 over 8 simplifies to 7 over 4. A cubed over a cubed is again 1. We don't need to write down multiplicative factors of 1. B to the 8th over b cubed, that's b to the 5th. Minus 12 over 8 simplifies to, let's see, if we take 4 over 4, we leave 3 over 2 behind, so minus 3 halves. A cubed over a cubed, that's a multiplicative factor of 1. We don't need to write those down. B cubed over b cubed, good golly, that's another multiplicative factor of 1, so we don't need to write that down. Our final term in this division has no variables in it. Woo, this looks like exactly the same problem we just worked. There must be something different. Do you see it? This problem has parentheses around 8a cubed b cubed. This problem does not have parentheses around 8a cubed b cubed. A lot of people imagine parentheses around 8a cubed b cubed even in this problem. Don't let your eyes trick you. There are no parentheses around 8a cubed b cubed. So we need to think about something. And what we need to think about is order of operations. And in order of operations, division and multiplication have the same priority. And what that means is, in the absence of grouping symbols, when we're performing several divisions and multiplications, we perform them left to right. For example, if we were looking at the simple arithmetic problem, 8 divided by 4 times 2, you might think that this is 8 divided by 8, but that's just not correct. Division and multiplication are performed left to right in the absence of grouping symbols. So what this really is 2 times 2, which is 4. This example that I'm working, so many people get fooled into thinking there's parentheses around 8a cubed b cubed that I've even seen problems like this worked incorrectly in textbooks. I promise you, if you ever see an example like this where they imagine parentheses around the 8a cubed b cubed in a textbook, the textbook is incorrect. You might want to check with your teacher about that. So, what's really going on in this problem? What's really going on in this problem is we are dividing negative 11a cubed b to the 11th plus 14a cubed b to the 8th minus 12a cubed b cubed. We are dividing it by something, but the only thing we're dividing it by is the 8. Now I need to multiply that result by a cubed b cubed, which I'm going to write over 1 to help me remember that numerators are multiplied by numerators and denominators by denominators. Now when I multiply these numerators together, I'm going to have to distribute the a cubed b cubed to every term in the first numerator. To help remind me to do that, I'm going to go ahead and put parentheses around the first numerator. I don't really need to do that, but it's a good reminder that I need to apply the distributive property. So let's go ahead and do that. When I distribute minus 11a cubed b to the 11th with a cubed times b cubed, I'm going to get a coefficient of minus 11. I'm going to get a cubed times a cubed, which is a to the 6th, and I'm going to get b to the 11th times b cubed, which is b to the 14th. Distributing the a cubed b cubed to 14a cubed b to the 8th, I get 14a to the 6th, b to the 11th, and doing my final distribution of a cubed b cubed, I get minus 12a to the 6th, b to the 6th, and this is all written over 8. Now some people may say this is a simplified expression because the only thing in the denominator of the fraction is a constant, but I think since we're new at this, I think I want to go ahead and break this up into 3 separate terms. So I am going to write another step where I'm writing a coefficient of negative 11 eighths times a to the 6b to the 14th plus a coefficient of 7/4. Remember, 14 over 8 simplifies to 7/4, multiplied by a to the 6b to the 11th minus 3/2 multiplied by a to the 6 b to the 6. Remember, 12 over 8 simplifies to 3 over 2. Now let's see, did we get a different answer here than what we got when 8a cubed b cubed was in parentheses? Well, take a good gander at this expression, and let's look at what we got when 8a cubed b cubed was in parentheses. Holy smokes, it's an entirely different expression. There's no a's, there's no variables at all in the last term, so it does indeed make a difference whether the denominator is written in parentheses or not. One last example, and the purpose of this example is again to kind of emphasize order of operations. Let's look at 5x to the 7th minus 7x to the 4th times 3x minus 7, all divided by 7x. A mistake I've seen people make is they'll take 7x and they'll divide it into the first binomial and into the second binomial. What's going on there is people are getting confused about the difference between multiplying fractions and adding fractions. The proper approach to this problem is to first simplify the numerator and then perform the division. And the reason that's the proper order is because fraction bars act like grouping symbols. They group the numerator separate from the denominator, so the first thing that we need to do is simplify both the numerator and the denominator. So going ahead and applying the FOIL method to the numerator, our first product is 5x to the 7th times 3x, which is 15x to the 8th. Our outside product is 5x to the 7th times negative 7, which is minus 35x to the 7th. Our inside product is minus 7x to the 4th times plus 3x, which is minus 21x to the 5th. And our last product is minus 7x to the 4th times minus 7, which is plus 49x to the 4th. And this is all going on over 7x. Now, the next step in this process is to break it up into the sum and difference of 4 fractions. I'm going to do that step in my head to encourage you, after you've done lots of practice writing out every step, to try and see if you can be successful doing that step in your head. So working that step, I would have 15x to the 8th over 7x. The coefficient would be 15 over 7. In terms of x's, x to the 8th divided by 1 factor of x leaves behind x to the 7th, minus 35x to the 7th over 7x. Minus 35 over 7 gives me a coefficient of minus 5. X to the 7 over x is x to the 6. Now we have minus 21 x to the 5th divided by 7x. So our coefficient is minus 21 divided by 7, which is minus 3. And in terms of x's, x to the 5th divided by x is x to the 4th. And finally, we have plus 49x to the 4th divided by 7x. The coefficient is 49 over 7, which is plus 7. X to the 4th divided by x is x cubed. Now, some of you may find success if you do go ahead and write this out as the sum and difference of 4 fractions, each with its own denominator of 7x. If you're more successful that way, that's fine. Write that step out. I do encourage you, though, after you've done several practice problems writing that step out, to try and see if you can be successful without writing that step out. If you can, that's great. If you can't, that's also great. You just need to write out as many steps as you need to write out to have maximal success. And that's it for my part of the lesson. Now I'm going to turn it over to Candace so she can shift the focus back to exponents.